Welcome back. In today's class, we will learn about two important theorems of Boolean algebra, or we can say of digital electronics, and they are De Morgan's theorems. And these theorems are very useful in simplifying Boolean expressions. So in today's class, we will be solving also Boolean expressions by using these theorems. These theorems were formulated by British mathematician and logician Augustus De Morgan, and as I said, these two theorems are very important to simplify Boolean expressions. The first theorem says that the complement of sum of Boolean variables or digital signals is equal to the product of their individual complements. That means if we suppose have two Boolean variables A and B, then sum of Boolean variables and then complement of that sum. So first we will take sum of these two Boolean variables, then we will take the complement of that, and that is equal to product of their individual complements. Individual complements means A bar, then B bar, and the product of their individual complements. Here, by sum of two Boolean variables, we understand or we mean as OR operation that we already know, and here product of their individual complements means we understand AND operation, which we have already learned in the class of logic gates. Next, we will use this De Morgan's theorem and we will simplify a Boolean expression. So our theorem is A plus B then complement, and that is equal to A complement then and B complement. So here we have OR operation and here we have AND operation. Now let's say we have two Boolean variables A and B. Say first we are performing NOR operation between these two Boolean variables A and B. So first OR and then NOT, so altogether it is NOR operation. And separately again I am writing this NOR operation. So first OR between A and B and then NOT, so it is NOR operation. Then what we'll do is the output, with the output of this NOR operation, again I will perform another NOR operation with A variable. So A, one Boolean variable, and the output of this NOR operation is another Boolean variable, and between those two Boolean variables again I am performing NOR operation. So first OR and then NOT on the whole operation. Then separately I am performing NOR operation between the output of these two Boolean variables. Since these two are Boolean variables, so output of this Boolean expression will be another Boolean variable. So with this output I am performing NOR operation with B variable. So first OR and then NOT, so altogether it is NOR operation. Then output of this whole NOR operation and output of this whole NOR operation, again they are separately two Boolean variables, and between those two Boolean variables I am performing again another NOR operation. So first OR and then NOT on the whole operation. And this is our whole Boolean expression that we will simplify next by using the De Morgan's theorem that we have learned just now. So what we can see, step by step we will think or we will simplify. So what we can see here, that between A and B there is a NOR operation, and what is the theorem? A plus B bar is equal to A bar and B bar. Now what we can see here is between A and between this Boolean variable, this means the output of this Boolean expression, there is a NOR operation, and between B and between this output of this Boolean expression there is a NOR operation. So it is in the form of A plus B bar, what we can see here in this theorem, and again it is A plus B and then again whole bar. So A plus B bar means we can write this way: A bar means A itself is A here, and B means A plus B then bar, that is altogether is our B in this case. So it will be written as A bar and then again b itself is a plus b bar. This is our b, and then another bar on that as per the theorem. Then we have an or operation here in between this, and then we will implement this theorem here also. So here b is our first boolean variable, so here it will be b bar, and then AND operation, and then the complement of the second boolean variable, and a plus b bar is our second boolean variable, means output of that operation. So we will be writing a plus b, then here bar, and that itself is our second boolean variable, and then a bar on that as per the theorem. And then or between these two operations we already have, that I have already written, and then on that we have this whole bar, so that we have to write or mention. Now, as per Boolean algebra, we know, suppose if we have a Boolean variable a, and if we have double complement on that, then that will be the Boolean variable itself. Means a, if the value of a is 0, then if we have double complement on that, so complement of 0 is 1, then another complement, and complement 1 of is 0. And if the value of this boolean variable is 1, and if we have double complement, then first if we perform the single complement on 1, then complement of 1 is 0, and then we have another complement, so complement of 0 is 1. So here a plus b, and on that we have double complement, double bar here, so that means result of that will be nothing but a plus b only. And here we have a complement, so here it will be AND operation between a complement and simply a plus b. And then we have OR operation, then b bar, so that will be written as it was, and then AND operation, and then we have double complement on a plus b, so it will be a plus b. And then on this whole operation we have another bar that we have also considered. Now what we will do, we will perform this AND operation between a bar and this OR operation. So a bar and a bar and a, and then we have OR. It's like simple multiplication. So a bar and then and b. So this is one operation, and then we have OR operation. So b bar and then and a. Fine. And then we have OR operation, and then we have b bar and AND operation. So this is another operation, and then we will have complement on the whole operation. So what we will do, again we will apply the concept of Boolean algebra. So a bar and a, we know that value is what? That value is 0, because if a is 0, then complement of a will be 1, and a itself is 0, so it will be 0. If a is 1, then complement of a will be 0, and a is 1, so it will be 0. So whatever is the value of that boolean variable, if we are multiplying the boolean variable and its complement, then always that result will be 0. So here this result will be 0, and here it will be a bar b, and from here this result will be 0 as it was. Then what we will be left behind from this second expression, it will be b bar a, b bar a, and then complement of that. Now a bar b plus b bar a, we know that operation is XOR operation or XOR operation, and complement of that is XNOR operation. So finally it will be a and b, and then plus a bar and b bar. This is the expression of XNOR operation, and this expression we can also obtain by using De Morgan's theorem. So let's do that. So now how it can be taken as a bar, and then we have AND operation here and operation here also. So a bar and b bar and a, and then between these two variables, because the output of this boolean expression will be a boolean variable as well as for this also. So here we are performing OR between these two outputs, or these two output boolean variables, and on that we have a complement. So finally we are performing a NOR operation. So here we can again apply or implement this De Morgan's theorem. So if we do that, then it will be a plus b and then bar. So it will be a bar. A itself is a bar b, and the whole thing is our first variable. So complement of the first variable, and then AND operation, and then complement of the second variable. So this. Now what we will do is we have to implement second theorem of De Morgan that we will be learning next. And as per that theorem, it will be complement of the first variable, which itself is a bar. So a bar is our first variable, and then complement of that, and then plus complement of the second variable, and then between them we have AND operation. So here again we have this NAND operation. So as per the second theorem, it will be complement of the first variable itself is b complement, and then we will have OR, and then the complement of the second variable. So from the first bracket, from first expression, what value we will be getting is a double complement. So it will be a only, and then we have b complement, and then from the second expression we will be having b only, because double complement of b, and from here it will be a complement. Then if we further simplify, then it will be a and then b, means a and b. Next is a and a bar, and a and a bar will be 0, that we already know, and then b and b bar, so that will be also 0, and then the fourth term will be a bar and then b bar. So we'll be having a bar b bar. So finally in the expression we will be having a and b plus a bar and b bar. Last part of this simplification will be more clear when we will learn the second theorem of De Morgan's. The second theorem says that the complement of product of Boolean variables or digital signals is equal to the sum of their individual complements. So again, if we have two Boolean variables a and b, then what we have here is complement of product of Boolean variables. So product means AND operation of those two Boolean variables, and then complement of that. So here altogether it is a NAND operation, and that will be, as per this theorem, that will be equal to sum of their individual complements. So individual complements means a bar and b bar, and then sum of that means OR operation. So what we can see here in the second theorem, on the left side we have here AND operation, or we can say altogether that is a NAND operation, and here we have OR operation, right? Next we will implement this theorem to simplify a Boolean expression. Let's say we have two Boolean variables a and b, and first we are performing NAND operation on those two Boolean variables, so a and b, and then NOT, so NAND operation. And separately I am performing or writing NAND operation on those two variables. Then what we are doing is we are performing again NAND operation between the output of this NAND operation and a variable or a Boolean variable. So this is one round of NAND operation, and then separately we are performing NAND between the output of this NAND operation and the second Boolean variable, which is b. So NAND operation, and then on the result of these two operations, the Boolean output variables that we will be getting, again on those two variables we will be performing NAND operation. So this is another NAND operation, and then we will see what simplified final expression we will get by applying De Morgan's theorem. Our second theorem says a NAND b will be equal to or between their separate complements. So here what we can see, we have NAND operation, here we have NAND operations. So first we will apply second theorem on this NAND operation, and if we do that, then it will be a bar plus b bar, and then between the output of this and a variable there will be NAND operation, and here if we apply second theorem, then it will be again a bar plus b bar, and then between this result and b variable there will be another NAND operation. and then we have another NAND operation on those two outputs. So if we further simplify, then it will be A and A bar. So A and A bar, and then we have OR operation. So A, then and B bar, and then we have this, and then separately it will be B and A bar, and then we have OR, then B and B bar, and then on that we have this complement. So this, then we have another NAND operation. So and then we have NOT operation. So what we can see here, A and then and A bar, so it will be 0, and what we will be left behind is A and then B bar, and then we have this bar, and here we have and from here B and B bar will become 0. So from the second expression we will be having B and A bar, and then we will be having this NOT, and on the whole operation we will be having this NOT operation. Next we will simplify as per the Boolean theorems. Now A and B bar, if we take that as our one Boolean variable, say y1, and B and A bar, if we take that as our another Boolean variable y2, then it's like y1 bar and y2 bar. And we have already learned the first theorem of demorgan's, and that was A plus B whole bar, and that was equal to A bar and B bar. So we can use the second theorem to simplify this part of the Boolean expressions. So here it is complement of one Boolean variable, which is y1, and then AND operation, and then complement of another Boolean variable, which is y2. So it can be written as y1 plus y2, then whole complement. So it will be written as A and B bar, which is itself is our one variable, then plus B and A bar, which is our second Boolean variable, and then this operation. So it satisfies the first theorem that we have already learned, and then on that we have already this whole complement. So we will be writing this bar again. So what we can see here is inside this double bar we have one Boolean expression, and definitely that will have an output, and that will be again a Boolean expression, and whatever is the value, since on that Boolean variable we have this double complement double bar, so this two bars will cancel each other, and finally what will remain is A and B bar plus B and A bar. So this is our final simplified answer or expression, and we know that is the expression of XOR or XOR gate. So this is how we can use De Morgan theorems to simplify Boolean expressions as and when required. In the next class, we will be learning something new. Stay tuned. Thank you.